So let's get started with our fast ML inference with Apache Spark. So what is that all about? And there's a big wall of text on here, and don't worry about that. I'm not going to read this to you because I know that's kind of the last thing you want is to dial into a webinar and then have somebody read to you off the screen. This is more for you to refer to later. Basically, the idea is that Spark is great for training or doing all sorts of compute across large data sets using a distributed compute cluster. So if you're dealing with a terabyte or even multiple petabytes of data at a time, and you're working with hundreds of nodes or even tens of thousands of nodes at a time in your compute cluster, that's where Apache Spark really shines. And when we're training some machine learning models, that's a great way to do it. And for certain kinds of ML inference, that can also be a good approach, but it doesn't cover every situation. And so a lot of projects run into trouble when they need to do fast inference using a model that they've already trained on just a small number of records. And so what I want to do is kind of describe the situation and bring you up to the state of the art on how we can solve that problem using Spark and other tooling. So just to be extra clear, if you are kind of new to this area in terms of terminology, so when we say machine learning inference, what we mean is using a model, and this is usually a model that's completely already trained, and we want to use that to make predictions on new records, right? So a classic textbook example is you have a spam filter that's already trained, and then you're going to use that filter to go and block some spam. Right, or you've got some kind of intelligent virus detection or network intrusion system, and you've already got it all trained, and you want to deploy it to alert you about suspicious connections on your network or suspicious downloads in real time. So some kinds of inference we can use Spark for because it kind of lends itself to this large-scale batch processing. So those are things like a lot of companies will send out a marketing email, and they may have an algorithm that decides which marketing email each customer should get. And it doesn't have to happen in real time. So they run this as a batch job, maybe in the middle of the night, and they look at, all of their millions of customer accounts and all the details about those customers. And for each customer, they're predicting what offer to send that customer, what products to promote, how good of an offer to give them, etc. And this can happen, like a large-scale batch job, kind of offline. And then eventually they generate emails and they shoot them out to all of their customers. So that if you're doing something like that, Spark actually works great for that, right? Because it's large scale and it's not real time. So what is the challenge, right? If that's the easy part, what's kind of the hard part here? So the hard part is that Spark was not designed to handle small data, low latency use cases. So those include things like credit card fraud detection, where you don't care about millions of customers, you care about a specific transaction, and you need to decide what to do with it very quickly, maybe in just a few milliseconds. If we're doing ad bidding, right? So you find out that you have access to a visitor to some website, you get some information about them, and you need to offer how much you're willing to pay to present an ad to that customer. And it's kind of a real-time auction situation. You have only a few milliseconds to do this to decide how much that customer presentation is worth. So there are lots of examples where you need to make predictions really, really fast on just a small number of records. And of course, there are lots of situations where you need to do both. You may need to use a model kind of offline and kind of real time. So what I want to do is kind of explain what the issue is here with using Spark for this fast situation. We'll kind of see how it goes wrong. And then what I'm going to do is I'm going to show you a number of approaches to trying to fix that. Unfortunately, a lot of companies that made a big investment in that Spark ecosystem have had a great success building machine learning models and doing their data engineering and data science, but then the deployment end of things has become a real problem, and you don't want to find that out after you've made this big investment. So what I'm going to do is I'm going to dive in and build a little model here. And I'm assuming for today, this is kind of an advanced topic, that everyone who's on the call already knows the basics of Spark and SparkML. So I'm not going to explain how to do Spark machine learning. That's a great topic, but it's probably for another time. Today I'm going to build a model. I'm going to assume that you more or less understand how that works, and we want to look at deploying it or doing inference with it. So I've got this input file right here. This is the diamonds data set from R. So you can see actually in the path here, it says ggplot2. So if you're familiar with the R ecosystem, you may have seen this data set before. It consists of about 60,000 diamond sales. And for each diamond, we have a whole bunch of information about that diamond. And we also have the price that it's sold for in US dollars. So I'm going to build a very, very simple model here today, a single variable linear regression, just considering the carat weight of the diamond, right? So, we can make a much better model, but that's not our goal today. I just want to make a very simple model really quickly, and we'll play around with that. So here I've got some code that reads in the data and trains a model over 3/4 of the data, and then we're going to save 1/4 of it for kind of validation. So we'll go ahead and run this. By the way, the notebook environment I'm using here is Databricks. This is the free Databricks Community Edition. It provides a really nice environment for playing around with this stuff. But everything that we're doing here today is pure open source. So you do not need to, you can use Databricks if you want, but you do not need to pay anybody for any of this stuff. And you do not need to use Databricks. All this will work on any configuration of Spark. So, okay, so I've got a model here. And let's just evaluate it, just as kind of a smoke test to make sure that it hasn't blown up and done something really weird. So my evaluator here says that the error is 1532, and that's a root mean square error. And that's about what I would expect for this data set, and for just the carat weight in a linear regression, 1532 is about what, about as good as you can do. It's not a great model, but it definitely has learned something. The standard deviation of the prices is about $4,000. So we've definitely learned something with this model. And now what we want to do is shift gears and say, okay, great. The data scientists and our team have built this awesome model. And now they've flipped it over to us and they've said, hey, maybe we're all the same people, but we've put on our other hats. And we now have to go and deploy this thing into production. So what we're going to do is generate some sample data that represents new diamonds. These are visitors to our website that want us to give them an online appraisal for their diamond or something. So we'll generate some demo data here. So you can see I just generated a Spark data frame that has 3 records in it. So there's a column called carat, which is the carat weight. And I have 3 diamonds in there, a 1 carat, a 2 carat, and a 3 carat diamond. And this is our kind of test data. So we want to see what does the model think about these new diamonds that we've got here. So I'm just going to flip my screen around here for 1 second. Great. Okay, so we've got our sample data. And how do we make predictions using the sort of standard Spark approach? I'll actually zoom my screen in a little bit. I know that depending on how you're viewing this, the resolution may not be that high. So I'm going to zoom in just a little bit, make everything a little bigger. So the standard Spark API for doing this would be to take our model object called .transform on our new data. And when you transform using a model, you get predictions. And if I call .show on that and run this job, you'll see that I've got a prediction column now. So over on the right, this is how valuable our model thinks the diamonds are. So the 1 carat is about $5,500. The 2 carat is about $13,000, and so on. If you know anything about diamonds, and I'll be honest, I'm no diamond expert. I know very little about it, but this model does have some problems on the high end, right? So it turns out that bigger, more expensive diamonds, there are other things that are much more important than the carat weight. So the accuracy of this model is better for the small diamonds for this particular model, if you're wondering about the $21,000. But that's okay, because again, we don't care too much about the actual numbers, but we care a whole lot about this, what I've just highlighted here. Notice it says command took 0.57 seconds. If I run it again, I could probably get it to run a little faster, but this prediction will take 200 to 500 milliseconds on average. And this is way, way too long for those low latency inference use cases that we might need to target, right? So just to kind of recap, this is fine if we're doing it late at night for lots of customers, but if we're doing, say, fraud scoring, we might need to produce an answer in under 10 milliseconds, right? And here you can see that even for just 3 records, and actually it's the same even for 1 record, it takes 200 to 500 milliseconds. So, okay, so why is that? So just to be really clear about the problem, Spark is designed for large-scale distributed processing. So when you tell it to do something, it spends a certain amount of time planning for a distributed, scheduled execution, even when that's not necessary. And when you're running this over millions of records, the cost of that planning is amortized over the millions of records. In other words, let's say you take an entire second to do the planning, but then you score 1 million records. Well, that's an average of only a microsecond of overhead per record. The problem is that if you're only scoring 3 records or 1 record, then that overhead is really big, and it kind of throws a wrench into the whole works. There's been some discussion that maybe in the future, Spark might be kind of re-engineered to work better in the small single machine kind of situation. But today, that's not how it works. So we've got this problem here. And it's especially ironic because this model, right, a single variable linear regression is just a single multiply and then a single add. So we're spending half a second on some, fancy server to do 3 multiplications and 3 adds, right, which should be able to be done in just a couple of processor clock cycles. So we're really, really not doing great here. We can see what the parameters look like, and even just in Python, we can do at least 10x, maybe 100x faster than Spark. So you can come in here and take a look at the model parameters, right? So there's the first coefficient is the 7749, and then the intercept. So we could use those numbers to generate predictions directly in Python, right? So here we can just hop into Python and say, show me C0 times the caret weight plus I for caret in 1, 2, and 3. And if we run that, you can see right away that we got 0.03 seconds, right? So we got more than a 10x speed up just going to Python and dropping Spark out of it, right? I can run this a couple times. It should be relatively consistent. So, so what this tells me is Spark is adding 10x, 20x, in some cases with a real distributed cluster, it would be even worse than what I've demonstrated today because we would be executing on remote machines. So Spark is adding 10x to 100x on top of just the raw Python inference. So, okay, so we've got this model, but Spark is clearly in the way. So now that we see what the issue is, how can we fix this? Right, so what can we do? So I'm going to run through a number of different options, and we'll kind of talk about the pros and cons of each of those. So the very first thing we want to try, probably the easiest thing to start with, is something called model.predict. So in the old days of Spark, the models had a predict method on them that allowed you to do a prediction on a single record without all of this distributed planning. And then in the newer Spark API, this method was hidden. It was made kind of a private method. So you could still kind of get at it if you knew what you were doing, but it wasn't widely known. And then in the most recent release of Spark, they've made it public again so that if you want to use this, you can do it. And it turns out that that's pretty darn fast, but it does have a couple of drawbacks. So the first drawback you might be noticing already from looking at the code. I said that there's a model.predict, but in the current version of Spark, model.predict only exists in the Scala and Java API, which means that if you're using Python, like most data scientists are, you need to do a little bit of dancing around here using the gateway that allows you to call from the Python control layer into the guts of Spark, which is all implemented in Scala. So I've written the code here that does that. If your data engineering team is working in Scala or Java, then you can just use this call directly. But from the Python side, what I'm doing is converting the value into a vector, and then I'm converting the vector into a byte array of something that I can deal with on the Java side. And then I'm going and using this gateway to call through into the Java side. So you can see here I take the model and I call this kind of semi-private Java object thing, and I call .predict on there, and then I pass a specially serialized version of the data. And once I've got that all set up, I can go ahead and do my prediction for each of these values. So you can see here, it's actually pretty quick, right? So it's almost as fast as the raw Python, and this, I'm not on a benchmarking platform here, so 20 milliseconds is maybe not a solid difference, roughly the same speed. So here I can make my predictions, and it's just running on the driver in Spark. It's not doing distributed computation or planning. It's nice and quick. It's relatively simple once you get past this little interface piece. So great, we're done. Cool. It's only 20 minutes and we're pretty much finished. No, okay. Not so fast. So this is a good step, but it's got some pros and cons, which I've summarized here, right? It is fast. It maintains the original model's compute semantics exactly. So this is actually a really big deal. We're going to see that when we go to move models around in the machine learning world, one of the challenges is to maintain the precise original semantics about feature engineering transformations, as well as things like the precision of the compute itself. And you might think, well, it's 2019, how hard can that be? But you'd be surprised, even within, for example, the TensorFlow ecosystem, if you, say, load a TensorFlow model up into TensorFlow serving, and you call it via the REST API, you get one number, and you call it via the gRPC API, you actually get a different number. It's approximately the same, but it's not really the same. And if you're controlling, say, the guidance system on a missile, that little difference is going to be a really big difference. So maintaining the compute semantics of the original model is a big deal. And in this case, we're able to get that exactly because we're using the original model code in Spark. Another nice thing is this doesn't require anything outside of Spark itself. So if you are in some companies, you may not be able to bring in outside packages, or it may take a really long time to get them approved, or in certain government and kind of defense applications, the whole kind of ecosystem has to be walled off, so you can't really just bring in random software. So having a system that works with just Spark is pretty nice. But there's also a bunch of drawbacks, right? So this API is only public in the most recent versions of Spark, so 2.4 and later. In 2.4, like we saw, it's only in Scala, so we need to go under the hood a little bit to use it in Python. The biggest problem is probably this one right here. So in Spark and lots of other machine learning systems, we want to build a whole feature engineering pipeline that includes feature pre-processing steps. So these might include things like standardizing or normalizing values, encoding discrete or categorical variables a certain way, doing embedding lookups, all kinds of other stuff. And when we use this API, we don't have access to any of that. It's totally up to us to do any preparation on the data record, and we have to give the model a vector of floating point values that are exactly what it would have gotten from Spark's own pipeline. But like I said, we can't use the pipeline stuff, so it's we kind of have to re-engineer that, and there's a lot of kind of risk and complexity in trying to do that. And then the last thing is that Spark is an awfully large and complex, and expensive to operate piece of software if we just need to do a multiply and an add, right? I mean, think about this for a second. We've got numbers, we're doing a multiply and an add, and we're bringing in hundreds and hundreds of megs of very complicated software, it's going to take up space to run, it's going to take up CPU cycles, it's going to expose, a security vulnerability surface, an attack surface that's much larger than we need. It's going to require operations people. And so the expense of doing it with Spark, even if we can, is maybe several orders of magnitude larger than what we want. So we're kind of wasting a lot of resources if we do it that way. Okay, so that's kind of the pros and cons of model.predict, right? It is fast, but it's not great. What else can we do if we want to stick close to Spark? So this is a relatively new piece of code that was released by Microsoft last year in 2018. And it opens up an intriguing possibility for a little bit more sophisticated way to expose our ML model as a service using Spark. So this project, this is called Spark, is it Azure ML Serving, I think it's called. I'll actually bring up the exact link here so that we can make sure we're all talking about the same thing. I'll show you where this lives. So let me just bring this URL up here. So this is called MLspark Serving, right? So mmlspark is Microsoft's open source Spark enhancement library for doing machine learning. It's maybe the best way to say it. It's actually a collection of libraries. So this is the Spark serving piece. And if you click to the top level project, you can see the pretty picture of sub-projects here. So these 6 sections in the middle of the page represent the sub-projects in Microsoft's mmlspark. This is open source, and so you can go ahead and use this. You don't need to buy any services or software from Microsoft to use this. It is part of the Azure system, so if you're using Microsoft Azure for your Spark or your machine learning, then this will fit right in. If not, you can grab the pieces that you want and maybe use them somewhere else. But this mmlspark contains the component that we were just talking about, which is the one in the upper right here, Spark Serving. And what is this Spark Serving thing? So what they've done is they've taken Spark Structured Streaming and they've created an adapter that allows you to make REST requests. These requests then feed through a Spark stream, and you get to do whatever you want in your streaming job. So following the normal semantics and rules of Spark Structured Streaming, you can do processing on the data, and in the case of machine learning predictions, that means take a pipeline model and do a dot transform, just like we did in the batch case. And the output stream will get linked up with the requests and then fed back to the requester. So it's basically a kind of a buffered REST request response wrapper around a streaming input and output system. So that gets you kind of halfway there, right? It gets you request response, but it doesn't get you the speed. To get the speed, we then have to use the continuous or low latency streaming feature. So this is a new feature that was added to Spark in 2.3, just about 1 year ago, that allows us to handle the scheduling differently on the cluster in order to get sub-millisecond throughput on streaming records. So just to kind of recap, what Microsoft has done is they've created a streaming source that you can make REST requests to. Spark works with this as a regular streaming source. You can do your normal streaming work. And then they've provided a streaming sink that you can write to from Spark that will represent the responses to these requests. It's kind of a clever idea. We'll see when we get to the kind of pros and cons. It is a little complicated. You can tell from how long it took me to explain it that it's maybe a little over complex. But it's kind of a cool idea. So let's go and take a look. I've got one cell here I'm going to run just to clear out checkpoint directories. And then here is the code. So if you're familiar with Spark Structured Streaming, and so that structured streaming is kind of beyond the scope of what we're going to do here today, but we do that in our other workshops. You'll notice that this follows a lot of the structured streaming normal patterns, and then it has some little extensions on there. So we start with a spark.read stream. We're using a continuous server here for our low latency. We've got some options that allow us to specify where we want to accept our REST requests. And we end up getting a data frame from this first chunk of code. Then we can do regular operations on that data frame. So here's our model.transform. This allows us to apply all of our pipeline model operations to whatever shows up in the data frame. And then we have this API that says we're going to make a reply from the prediction column. So what this is saying is that the output from the call should be the content of the prediction column after we've done this transform. And then we're going to go ahead and take this replies data frame, and then we're going to write it out. So you'll see the usual write stream and trigger, query name, checkpointing. and a couple of other pieces that are maybe unusual, like the reply to is not the usual API. So let's go and crank this up. So now we've got this streaming job running here. And we can come down here, and now we can make REST requests to it. So here you can see that we're just building a post request with some JSON data. So we're going to take the numbers 1, 2, and 3. We're going to make a JSON document that has those as caret values. We're going to post it to the URL that we specified above, and we'll print out the response. And if we go ahead and run this, the first hit takes a little while. You can see this is 1.24 seconds, but once it's spun up, it should actually be pretty quick. So you can see when I hit it the second time, 0.07 seconds, 0.08 seconds. So this is pretty quick, especially considering it does use parts of the network stack, although it's localhost, so it's not really going over the network. Okay, so what have we accomplished here? We've taken our traditional Spark machine learning pipeline, and we've embedded it into a streaming server that has a REST adapter connected to it. And we've shown that we can now send simple JSON requests and get nice, simple JSON responses. And we can do that really fast. And we can use all of the nice Spark APIs and tools that we're used to. So that's definitely an advance over the last example. Let's stop the server here, and we'll kind of sum up the pros and cons. So I claim that this is much better because it allows us to reuse the feature engineering pipeline and maintain all of the semantics of our feature engineering transformations. So what are the pros and cons? We get the pipeline, that's great. It uses native Spark APIs, right? This is great. And it offers a fast REST service. That was kind of the whole point here. But there are also some cons. Right, so it still involves deploying a large software platform to perform small, limited operations. Right, we're still deploying this enormous platform when we don't really need it. We need this unusual architectural adaptation. So the idea of using structured streaming and kind of gluing a request response thing onto it, it's innovative, but it's also a little weird. I mean, people do that, but it has a little bit of a smell to it. Relies on experimental continuous streaming mode. So the continuous streaming is something that's, like I said, only a year old. It's marked experimental. It's one of those things that kind of use at your own risk. So it's not necessarily a rock solid solution for enterprise production use cases. And probably the biggest issue is this one down here. There's a lot of complexity here for something that's a multiply and an add. One of my mottos for all data engineering work is never use streaming for anything if you don't have to. Because the operational requirements of a streaming app are basically everything you need for a regular app, plus a whole bunch of additional complexity to keep that stream running and the timing right. And if you can avoid streaming in any way, it's almost always worthwhile to do it. If you are going to use streaming, then you probably want to treat it as a first-class citizen and think of the architecture as being a streaming app architecture. And here we've got all of the complexity of low latency structured streaming, this weird adapter pattern on top of it, all of the Spark platform underneath, and we're not even treating it as a streaming app. It's like we're trying to pretend that it's not really streaming. And there are things that can go wrong with streaming that, if you hide, then you will have succeeded in hiding them until they break. And then all of a sudden, you'll be up in the middle of the night trying to fix something. So I'm not 100% sold on this approach. I think it's a bit over-engineered for what we're trying to do. That said, it is pretty cool that we can take this library, throw it on there, and use all of these Spark components to accomplish this task that otherwise we wouldn't be able to do. So, okay, if this is not perfect, how can we go further than this, right? It seems like we've kind of gone about as far as we can with pure Spark. And that is correct, right? So it turns out that in a kind of a pure Spark environment, we can't really do too much more. The solution, in terms of getting a better solution at this point, is to take our model and get it outside of Spark. right? So the fact that we're using Spark to train our model over lots and lots of data does not mean that we need to use Spark for inference. So what we've got to do is pick some mechanism that will let us export or extract our model and ideally our whole processing pipeline from Spark and run it somewhere else. And that's arguably hits a few more of the bullet points that we'd like to target, because now we can use a runtime that is smaller and more lightweight and more efficient, and maybe can run in more constrained environments. And hopefully we still have all of the nice semantics from our original Spark model. So what are a few ways to do this? The first one I'm gonna demo here is something called MLeap. So MLeap has been around for several years, and it was originally created in order to solve this problem, and has later expanded to support models from scikit-learn and TensorFlow as well. And the idea is that we take those models, the scikit-learn, the TensorFlow, or the Spark, and we export them into a format called an MLeap bundle. And the MLeap bundle is this artifact, basically a zip file that we can take to another location and use it with the MLeap runtime. So an MLeap runtime is a very lightweight chunk of JVM code that we can either use by itself. There's a free server you can just download, or we can embed it in our own apps. It's all open source. If you have anything that runs on the JVM, like let's say you've got some servlet-oriented app, you can throw the MLeap code in there and do your inference right in there. So that's what MLeap is all about. And I'll show you how we can export our pipeline model once we've installed MLeap. So we have to install all of the Java and Scala bits of MLeap and then the PySpark wrapper to make sure that's working. And then what we're going to do is we're going to use this class called Simple Spark Serializer from the MLeap library, and that's going to allow us to serialize our model. So I'm going to delete this from maybe the last time I was playing around with it. And then here's the key line that we're looking at. We're going to take our model and we're going to go serialize to bundle. And we're going to specify a path where we're going to write this out to. And we're going to supply our sample data so that MLeap understands the schema of the data frame that we're working with. So MLeap kind of needs to know the predictors and their type and how all of that stuff fits together. And we will get from this, hopefully, an MLeap bundle. So let's take a look if we've got one here. Here it is. So this is the MLeap bundle that we just produced. So it's about 2,500 bytes here. And once we've got that, we can use this separately from Spark to do all kinds of machine learning stuff. If you contact Endpoint, we can follow up with the links to the documentation on MLeap. Basically, they have a proxy or kind of a miniature version of a data frame called a leap frame. And so the idea is that you can put your data into a leap frame, and then you can do all kinds of data frame stuff with it, including running the model, and it doesn't depend on Spark. It's a much more lightweight, local implementation that's made for these small data use cases. So that's the MLeap bundle. And here are kind of the pros and cons for MLeap. So you maintain Spark semantics. We separate the model from the Spark platform, so that allows fast scoring in lots of other places without requiring Spark. It's got a multi-year track record, so it's been around for several years. It's also supported by the new MLflow platform, which was created by some of the same folks that created Spark in the first place. They support lots of formats with MLflow, and this is one of them. It's free and open source software, and it also supports scikit-learn and TensorFlow models. So that's pretty great. There are a couple of drawbacks. It only runs with the MLeap runtime. In other words, it's not really an industry standard format. It's not like there are 10 companies that all offer MLeap bundle servers, right? If you want to run the MLeap model, you need the MLeap code, which kind of produces kind of a little bit of a dependency there. It won't interoperate with other tools outside of its own ecosystem. So we said there's Spark, TensorFlow, sklearn. But what if you've trained a model in R? right? So let's say you've gone into R and you've built some GLM. Well, how does that fit in here? Well, now you're going to have a challenge because you're going to have to somehow move that model. Probably the easiest thing might be to re-implement it in TensorFlow or something like that. But in any case, it's a little bit of a limited ecosystem. And it's not a huge open source project, right? It's a nice piece of work. It works well. Lots of people use it, but it's not huge. It's not on the scale of something like Spark or TensorFlow. So there is a little bit of risk because you can imagine, in 5 years, even if they're not the latest and greatest, Spark and TensorFlow will still be around. It's hard to know whether, say, MLeap will still be around and whether it will, be up to date and there'll be bug fixes and so on in 5 years, just because with small OSS projects, it's really hard to predict that sort of thing. So now, having said all of that, if a company asked me today, what's the best candidate for kind of simple, fast inference production deployment of Spark models, probably MLeap is the right answer. It has a lot of benefits and relatively few drawbacks. We'll see some other options in the last section of this webinar in just a minute, but they're not, none of those are sort of perfect. This is probably the easiest or the go-to solution today, although it may not be the go-to solution in the future. Now, in this example, what I've done here today is just shown how you can take your Spark pipeline and export it with MLeap. I haven't really shown using the MLeap bundle for scoring, and that's just for time reasons. If you want to see an example that shows the deployment, I've got a YouTube tutorial that shows the whole thing end to end. The last 5 or 6 minutes shows deploying this into a totally separate VM that has the MLeap server and Docker, but no Spark stuff, so you can take a look there. So if you came here today just looking for a quick answer, this might be the place to stop. But I hope that you're interested in one more topic here, which is, can we go to an industry standard model format for deployment, right? So it would be nice to get all of these benefits and not be tied to a small project that has its own format, because there's always some risks there. So there's probably 3 industry standard formats for machine learning models that are worth considering. And we're going to kind of talk about all 3, but we'll drill down on just one. So the first one is PMML, or Predictive Modeling Markup Language. This is kind of the granddaddy standard format. It was created around 1996 under the auspices of the Data Mining Group. It's widely supported by proprietary machine learning tools, so things like FICO and SAS and other kind of non-open source tools. It has some support in the open source world. Probably the best support is from R, which can export a lot of models in PMML, but it's a little spotty. Like almost no permissive open source tool can really import this stuff, which makes it a little bit tricky. So here's kind of the good and the bad, right? It's XML based, so it's pretty easy to deal with and human readable. Very widely used and very well known in the industry. So there's, it's not some sort of strange, peculiar technology, and it's relatively interoperable. So, maybe not perfect, but there are a lot of tools that can read and write different formats of PMML. So that's kind of the good. The bad is probably the biggest headline is that Spark itself does not support exporting ML pipelines as PMML. There's kind of a lot of backstory to this. The old version of SparkML from like years ago did support PMML export, but only for the models, not the pipelines. There's also a set of JIRAs in Spark currently for adding PMML support, but in all of 2018, we just kind of got some scaffolding and maybe one kind of model. So there's not, it's kind of a placeholder, and it's not clear whether there's enough interest in the Spark community to actually build this out. So I wouldn't, especially if you have a business need today, you need some solution today. If you have a business need tomorrow, I'm not sure I'd wait for this. There are tools which allow Spark pipeline to PMML export. You'll see that all over, but here's the catch. They're almost always using something called JPMML. So JPMML is a really nice chunk of code, and that project supports PMML interop between almost everything in the universe, and also includes a really nice PMML runner. But the catch is that on the open side, it is licensed under AGPL. So AGPL, or the Afro GPL license, is a very difficult, non-business friendly license to work with. So, you know, for academic and demos, this works great, but when you need to actually do your license audit for legal at your company, this is not going to work, because it's almost impossible to work with. So that leaves you with doing a commercial license. And the problem with the commercial license is the company that makes this is very small. And so most large companies are not really able to kind of build software systems that rely on commercial licensing and support from just a very, very tiny company. There's no community, and then there's also no big company to fall back on. So it kind of creates this difficult situation. That may change in the future. Maybe there'll be third parties that effectively license JPMML and are able to provide support at scale. But I'm not sure that there's any of those that can convincingly do it right now. And this is kind of a variation of the same issue, right? There's no permissive, open source, widely used, high performance library for serving these models, right? So there's proprietary tools for doing it. There's Afro GPL, there's all this other stuff. But if you want, and there's even an old version that's BSD licensed, but if you need fast, open PMML serving, there's pretty much nothing there, right? So this is kind of the challenge with PMML. So the summary is it might be right for you, but it's going to require considerations on the business and legal side that are outside of the technical. The next major standard we might want to look at is something called PFA. PFA stands for Portable Format for Analytics. This is intended to be the successor to PMML. It's also from the data mining group. It was created around 2016, and it has a lot of advantages over PMML. It has well-known semantic and security guarantees. It's almost like an entire little math platform. So it's a wide platform that can do almost anything with math, but it's restricted to, again, math and some basic control flows. So you can do a lot, but not too much, is the idea with PFA. There are open source and nicely licensed, permissively licensed implementations for JVM and Python. So we don't have that, no way to run this kind of situation. Let's see, as I mentioned, it can do a large variety of operations, and it also has interchangeable binary and human readable representations. So this is really nice. Like there's an Avro representation for models that's compact and has schema defined, but then there's also YAML and JSON versions that are human readable that you could use if you needed to diff or store versions of your models in some kind of a content system. So it's got a lot of nice features there. The cons are that it's new, so there's relatively little industry support so far. There's very few products that have any PFA support. On the Spark side, there's a project called Aardvark from IBM open source that came out last year. And the goal of this Aardvark project is to support SparkML export to PFA. So this is very exciting, but the challenge is that so far there's only been a single public release. That was about 7 or 8 months ago. It was an 0.1 release that doesn't really have enough to be fully usable, and there's not a big community around it. So there's a lot of promise there, but so far the momentum isn't really there. So I wrote PFA might be the future, but it definitely isn't the present. And that brings us to the last topic here. So the last one I want to discuss is something called ONNX. So ONNX, or Open Neural Network Exchange Format, this was originally created about 1.5 years ago by Facebook and Microsoft, just as a format for importing and exporting neural nets between different neural net toolkits, different deep learning tools like, say, Caffe and PyTorch and so on. The crazy thing is that this has picked up a lot of momentum in the last 1.5 years. So on one hand, it's expanded to include support for traditional machine learning models, right? It was originally just about neural nets. Now it can do all kinds of machine learning. And on the other end, originally it didn't have a standard runtime. It was just a file format, right? But now it has a whole bunch of high performance runtimes. So Microsoft has an open source runtime, which I'll demo, that supports CPU and GPU acceleration and runs on different platforms. And there are even a whole bunch of hardware optimized implementations. So Intel has a runtime, Qualcomm has one, there's a few other ones out there. So ONNX is kind of like the big surprise story of 2018 that really went from nothing to arguably being the kind of most advanced deployment format, kind of standard deployment format within about a year. Now, if this is so great, why didn't we start with this at the beginning? Well, ONNX has really solid support for all of the neural net-based stuff, but the traditional machine learning and import-export with things like Spark is just starting to come out. So there is like a basic Spark export for some pieces, but that's really new, and the same thing with scikit-learn and some other models. So that's why I'm hesitant to commit to this right now, because some things don't work yet, and I want to make sure the momentum gets us where we need to be. But it definitely has the most exciting trajectory at the moment, and I thought since it's new, this would be a fun thing to demonstrate here. So what I've done is I've built another model. This model is a logistic regression model, so it's a classifier instead of a regression model. And what we're doing is we're just going to predict whether a diamond is expensive, and we're going to define expensive here as being over $10,000. So I'm just going to take my data and I'm basically going to train it against this binarized label here, which I've called pricey. And it's going to decide, it's basically going to learn to predict whether a diamond, based on its carat weight, is worth more than $10,000 and associate a probability with that. And then we'll show how we can export this using ONNX and how we can run this in another environment. So first we'll go ahead and train up the model. Okay, so now we have our model. Then we'll go and evaluate it just to see how it's doing. And the default metric here is accuracy. So our model is accurate about 97.6% of the time as to whether a diamond is pricey or not, over $10,000. And then here's the fun where we get to export as ONNX. So I'm using a library called onnxmltools, which is part of the ONNX project. I'm going to do some imports from there. And the key piece is I'm going to run this function called convert SparkML. I'm going to give it the model, a little name label here. And then for the schema, I'm going to use this helper called build initial types simple. So for simple schemas, you can give a data frame to build initial types simple. That will provide the schema data. And the output from this should be a ONNX model object. So let's go ahead and run that to make sure I get my imports. And then we can build a model. And now we're going to write this thing out to disk. So I'm just going to take this model, I'm going to write it out to temp/diamonds1.onnx. And then what I did in order to demo this on another machine is I copied it to a location in the Databricks file system. This is kind of a footnote that's not super important, but it allows me to download this through the browser. So I can copy this over. And then I was able to download. I did that before the demo today, so I've got it all set for you. I've downloaded this file and I've loaded it up onto another server. You can see the file sitting here. So the diamonds model looks like it's 514 bytes, and it's sitting over here in my file system. So that's kind of the end of the notebook piece, but I'll show you how we can use this and serve it. So what I did is I went over and flipped up a just a little Ubuntu machine in Amazon Lightsail. So here I've got my Amazon Lightsail server, and I've got, if you look here in my home folder here, you can see my diamonds1.onnx file. And then I wrote a little service that will serve that up. So I'll show you what that looks like. So this is the entire server. You probably don't want to put this into production. It's using a little library called Responder, which is a Python library for exposing services. And it's also using this Microsoft library called ONNX Runtime. So we load up the Microsoft ONNX Runtime. We attach the runtime engine to the ONNX model right here. Then we have a little bit of boilerplate code that sets up a web server. And it binds a route that starts with /caret and then some carat weight. And then what we're going to do is we're going to take that caret weight, which is coming in as a string. We're going to create a float from it. We're going to create a NumPy tensor from that with the appropriate shape. And then we're going to feed a request with the caret predictor name and this tensor into our ONNX model. And in real life, you would actually tell ONNX runtime exactly what output you want. In this case, I'm putting none because I want to see all the outputs. So what we're going to do is we're just going to get a string back on the screen that shows us the prediction and the probabilities. So that's the entire server. We can spin this guy up if we go, let's see, I got to switch to my right conda environment and activate ONNX 1. And now we should be able to spin this up. So, okay, so what does this look like? Well, we can hop over into a web browser and hit this server and see what it looks like. Let's see, what is my public IP here? I have to go figure out where that is. There it is, 54. I'm just going to build up a little request for us here. 54.149.230.216/caret. And let's ask for a diamond that's 1.6 carats. And let me just bring, you can see the request coming through there, but here's the actual window. So here I can go in a browser and I can make requests to this, and you can see that the prediction for this diamond is that it's expensive. The probability of it being expensive is 60%, give or take. And I can change this around, to make other predictions. So, 1.4 carat diamond is only 27% likely to be expensive. So you can see the whole thing is connected together. The very last thing I'm going to show you is how fast this is, and I don't want to include the round trip time from my computer here in San Francisco to the Amazon data center in Oregon. So what I'm going to do is I'm going to background this guy, and then we should be able to make some requests locally, and we can see what that looks like. So we'll run this with the time command, and we'll just see how long this takes here. So there, you can see that if I'm basically just running through the network stack, but just localhost, so not really over the network, you can see that once this thing is actually up and going, we're looking at 7 milliseconds for this response. So this gets us where we want to be, right? So we took a model, we built it in Spark with potentially a large amount of data. We've exported the model, actually the whole pipeline, so including the pre-processing from Spark into another format. We've used a format that is an industry standard that has lots of different runtimes that work in lots of different environments and has many, many companies supporting it. And then we've been able to go and deploy this into another environment, in this case, a server that doesn't know anything about Spark and just happens to have some Python tools on it. And we're able to get a service that returns results in the single-digit milliseconds. So that's kind of the whole goal of what we wanted to look at today. Hopefully, this will be useful in planning and delivering your own machine learning systems. And I'm going to pretty much wrap up here.